Okay, can everyone hear me? All right, thanks everyone. I'm David Bruns-Smith. I'm a postdoc at Stanford, and this talk is going to be about our paper, Augmented Balancing Weights as Linear Regression. The archive link is here, but this paper is also forthcoming as a discussion paper at JRSSB. And so if you find this particularly interesting and want to be a discussant, send me an email and I can pass that along to the journal. This is joint work with my advisor, Avi Feller from Berkeley, and then also Betsy and Oliver. So to give a quick summary of the talk at a high level, it's well known that machine learning is biased. So I'm focusing on the case of sort of very flexible high-dimensional linear models that are regularized, like x beta hat. And one way of understanding this is that the residuals, y minus x beta hat, are bigger than they possibly could be in sample. This is good for prediction. This is not an accident. You do this on purpose, but it can be bad for estimating the average treatment effect. And it's also hard to get standard errors because usually this bias doesn't go to zero asymptotically. One solution to this problem is called undersmoothing. So you just choose a new model, beta hat, that just fits more. It has less regularization. And in this linear setting, you're going to end up with coefficients closer to the OLS coefficients, and then you can have less bias. Another solution is debiased machine learning. So here you correct for the residuals explicitly. Our result is going to be to rewrite debiased machine learning as a plugin of an outcome model, beta hat aug, which is also closer to beta OLS. So here it looks just like undersmoothing. And in fact, in some conditions, we're going to show that they're numerically identical procedures. So that's a high-level overview of the talk. And I just want to say that we found this to be a super fruitful framework. So this idea of taking debiased machine learning and thinking of it as unshrinking your original outcome model towards OLS has just been useful for reasoning about what's going on when you run debiased machine learning. In this paper, we use it to investigate hyperparameter tuning. So just one of the things that comes up is we find settings where actually debiasing gives you strictly worse finite sample mean squared error, which is sort of surprising. But there are many other downstream results. So we use this setup to find connections with multi-calibration and theoretical computer science, the TMLE, synthetic controls, et cetera. So I hope this, just before I get into the results, I hope I can convince you that it's actually useful. So we're going to start with just a quick review, mostly introducing notation about using machine learning to estimate the ATE. So I'm going to use a totally standard missing mean setup. So we have a treated group that we're going to denote by P, where we observe covariates X and potential outcomes Y1. We want to transfer that to the entire population, which we'll write Q, where we observe covariates X, but Y1 is missing for the control units. And we're going to try to estimate this mean, which is partially missing and is equal to half of the ATE. So as review, one of the ways of doing this transfer problem is fitting a machine learning model. So you train some model in the treated group, M hat. You then use that to predict the missing values in the full population, and then you just plug it into the functional that defines your estimate. And in this case, it's just taking the sum. So this is going to give you a biased estimate because M hat is regularized for prediction. So again, to fix a particular setting, I'm going to consider sort of high dimensional regularized linear models, XP beta. So you can think of like the ridge or the lasso. But I typically have in mind a very high dimensional setting. So an RKHS would be fine, infinite dimensional linear space, that's okay, or like a last layer embedding from an LLM. And I'm going to use this little cartoon to think about regularization. So we have some regularization, hyperparameter lambda. As you move lambda towards zero, you fit y minus x beta as aggressively as possible. That's going to give you the beta OLS coefficients. As you regularize more, you fit less. And so the residuals y minus xp beta are going to be larger. This bias is going to pass through to our target estimate. So larger residuals means that when we do this plugin, we're biased for our target. As a result, the estimate's not going to be asymptotically normal, so we can't get the usual standard errors. I think in applied work, this is like a really central concern. But also, even in finite samples, it's possible the optimal bias for prediction isn't equal to the optimal bias for the target estimate. So this bias can actually make you perform worse in finite samples as well. One solution to this issue is to do undersmoothing. So if we go back to our graphic, we have our regularized coefficients, beta hat lambda. One suggestion is, hey, just use a smaller lambda. We have some lambda prime smaller than lambda, and that means that we're going to be fitting more aggressively. This has been studied really extensively. There's lots of recent work. And just a note on the name, traditionally this literature was about bandwidth choice for a kernel smoother, and I think that's where the term undersmoothing comes in, or the number of bases in a sieve. But maybe in a modern setting, we would just call this overfitting. So you use overfitting to have less bias than you plug in. The question is, of course, well, how do you pick lambda prime? And people have thought about this, and there's this Bruce Hansen quote, "It is unclear how to pick this suboptimal hyperparameter. I call undersmoothing a dirty trick because it is slipped in by authors to make their results cleaner and derivations easier." I don't necessarily 100% agree with this quote, but we can, at least it suffices to say that this is hard to use in practice. And we'll return to that later in the talk. Another solution is debiasing. So debiasing just takes the baseline machine learning outcome model and then corrects for the residuals with this correction term. So if you compare that to undersmoothing, when we undersmooth, we just mechanically made the residuals smaller by regularizing less. And debiased machine learning, we just correct for them after the fact. Importantly, we correct for the residuals only in a very particular direction. These are the IPW weights, 1 over the propensity score. But you can also think of them as this density ratio between population and the treated group, or the Rees representer of our particular functional that defines our estimate. So these are all equivalent ways of thinking about what this W is supposed to be. In this paper, we're going to consider using a very particular estimator for W, which is called balancing weights. So traditionally, one would estimate the propensity score, E hat, and then invert it. So you get a sort of plug-in estimate of W hat by taking 1 over E hat. And balancing weights, you just target those weights to estimate 1 over E directly. So we're not going to do this sort of plug-in and invert. We're just going to estimate the weights directly. This goes by many names. It's been proposed many times in different fields, I think just because it's a good idea. It goes back to the survey calibration literature. In computer science, it's called direct density ratio estimation, balancing weights. And then recently, it's someone has proposed the name Rees regression, which I really like. I think I came to this problem from balancing weights, so I've always called it balancing weights. But in retrospect, if I were to write this paper again right now, I'd probably just call it Rees regression. Similarly, using these balancing weights to do debiasing is a really old idea. So the earliest possible instance of this exact algorithm being used was the GREG in 1992, but also there's a paper called approximate residual balancing, which does the same thing, or most recently, automatic debiased machine learning. Again, probably instead of augmented balancing weights, if I were to write this paper right now, I would just call it AutoDML, but that's just the particular literature I came out of. So a very terse review of some of these ideas. Just as for the outcomes, we're going to consider regularized linear weights, W hat, which are linear in X with coefficients theta, and which directly estimate 1 over E. How do we do this? Well, we just solve for weights that enforce this particular condition, sometimes called a balance condition. So it's weights that are applied to your treated covariates and return the covariates in the whole population. So we'll call this quantity on the left xq hat, this quantity on the right xq bar. So why does this work? Why does this estimate 1 over E? Well, one way of seeing this is that this difference between xq hat and xq bar in the population is just equal to x theta minus 1 over E. So these are just exactly your residuals times x. And what happens when you have a residual times x? Well, that's just the normal equation. So that's why this is Rees regression, because this is implicitly enforcing the first order condition from doing least squares regression of x theta on 1 over E. So I'm going to call this thing on the left Riesz residuals. Of course, it's not the residuals because 1 over e is not observed. So we don't observe the true residuals, but it's the normal equation violation. So you can think of these as sort of spiritually residuals for this regression problem. I just thought of this setup recently, so hopefully this makes sense to everyone. I haven't tried presenting this particular version before. Regularization means you get larger Riesz residuals. So we have a very, very similar graphic. Now we have a regularization parameter delta. As you regularize less, as delta goes to 0, then you're just enforcing directly that xq hat is equal to xq bar. As you regularize more, you don't enforce this position, this condition, and you're going to get something with large residuals that's very biased. So this should look just like the outcome model slide. And in fact, I could have started the other direction. I could have started with weighting, and then we would use prediction to debias the weights. Either viewpoint works. So our new result is to write down debiased machine learning as a form of undersmoothing. And maybe I should pause for questions here. Is there anything in the chat, or should I keep going?
There's no question yet, so please
Great.
keep going.
All right. So our main result takes this debiased machine learning estimator with linear outcome model and linear balancing weights and rewrites it as a new outcome model that we're going to call beta aug. This has a very particular form. It's an element-wise convex combination between the original outcome model beta hat lambda and the beta OLS coefficients. And these convex combination weights have a very particular form. It's just the ratio of xq hat versus xq bar. So if you recall, xq hat was the weights applied to the treated covariates. This is just a measure of how well you enforce this balance condition. It's the Riesz residuals written as a ratio. And this lets us think of debiasing as doing some type of unregularization. So if you think about that delta hyperparameter for the weights, as you drive that hyperparameter equal to 0, you set xq hat just equal to xq bar. That means that A delta is identically 1 everywhere. And actually, debiased machine learning is just identical to ordinary OLS plugin. That recovers the famous OLS is doubly robust result from Robbins et al. 2007. And you can actually think of our paper's result as being a generalization of OLS is doubly robust. At the other extreme, as you just regularize W away, so you move delta to infinity, then A delta is going to go to 0, and you just recover the original outcome model. And that makes sense. Basically, if you're adding a bias correction term that scales with the weights, if you regularize those weights to 0, you're just going to not do any bias correction at all. But in general, you usually pick this hyperparameter delta to be somewhere in the middle, and you'll end up with some combination of beta lambda and beta OLS. It's going to be closer, but not all the way unshrunk to OLS. So the natural question then is, well, how does this compare to traditional undersmoothing? It looks a lot like it. So in traditional undersmoothing, we just moved mechanically our machine learning estimator to be closer to beta OLS by choosing a smaller value of the regularization parameter. How does this compare to our beta aug? Both moving towards OLS, but are they doing it in the same way? Is the question. It turns out that when you do everything in an L2 penalized model, these viewpoints are identical. So ridge regression, a common way of writing it is to take the beta OLS coefficients and you're doing some type of shrinkage that's targeting like the inverse covariance matrix in a particular way. If you debias that with weights that also use an L2 norm penalty, we get beta aug that has exactly the same form as ridge. So we're shrinking beta OLS, but with a new hyperparameter. So instead of lambda, we have a hyperparameter gamma. And gamma has this particular form where it's everywhere smaller than lambda. So this is just exactly classic undersmoothing for ridge regression. Our mnemonic for this is ridge plus ridge equals ridge. So this viewpoint allowed us to make some progress towards thinking about hyperparameter tuning for debiased machine learning. So if we go back to this quote, why is undersmoothing so hard? Well, because it was hard to pick your lambda prime. we had our original amount. Maybe you pick lambda with cross-validation. That's easy to do, but you're supposed to choose something smaller than the cross-validated value. How do you actually do that? Our result for ridge says, well, this is just equivalent to taking the hyperparameter for the weighting problem. So you can view this positively. Maybe this is a way of making progress towards undersmoothing by reasoning about how much do you have to regularize the weights to get them to converge. You can also think about this negatively. You know, if the original problem with undersmoothing was we don't know how to pick this hyperparameter, maybe this is telling us we don't know how to pick delta either. We're trying to make progress towards a good choice of delta, and so we think about that a little bit in the paper. So we explore this both asymptotically and in finite samples, and I'll give a quick preview of some of those results. So one way of trying to make progress towards hyperparameter tuning is to look at RKHS asymptotics. So there's lots of recent results looking at ridge regression type things and reproducing kernel Hilbert spaces. There's results for debiased kernel ridge, and usually these have a double kernel ridge form where you use a kernel ridge outcome model and kernel ridge for the weights. Typically, those results show that if you have a hyperparameter schedule that's around into the 1/2 for both the outcome model and the weighting model, then you get something that's asymptotically normal. There's a separate literature that does undersmoothed kernel ridge. So it's when you have some particular ATE type estimand, you fit a kernel ridge outcome model, but instead of doing cross-validation, you set lambda prime equal to something that shrinks as 1/n. So you use much less regularization than you normally would. It turns out you can prove that this also converges to an asymptotic normal distribution. So our result just mechanically, if you do the calculation for gamma and you plug these two rates in, you're going to get something that also is just ridge, but with a hyperparameter that shrinks as 1/n. So we nicely show that these two separate literatures actually have the same kind of basic perspective. One thing that I thought was interesting is that this undersmoothing result never thought hard about the weighting problem. So it never thought hard about modeling the density ratio or the propensity score. It never showed that you needed to converge to something that looks like the propensity score, but you still managed to get asymptotic normality and semiparametric efficiency. And so that led us to this idea that, well, you can just cross-validate lambda and then just set delta equal to whatever hyperparameter you used for the outcome model, and you're going to have the right rate for debiasing. And it turns out that this works really well. So it's a kind of strange result that says that when you're working in L2 type spaces, L2 penalized top spaces, you don't need to think so hard about the selection model. There's something that just reduces everything to thinking about the original prediction problem. I'm not really intuitively sure how that works. So there's still more to be done, I think, in terms of just understanding what's going on here. We can also get the finite sample bias and variance. So there's been lots of work on finite sample analysis of ridge, and the fact that debiased machine learning in this L2 type setting is just equivalent to ridge means we can just grab that stuff off the shelf. So I don't expect you to actually parse what's going on in this slide, but the key is that we can just literally write out the finite sample bias and variance for ridge in a well-specified setting. One of the interesting things is you can just analyze this thing numerically. We can construct instances where actually more bias is optimal for the ATE than for prediction. So this means that if you do debiasing on these particular instances, you're actually going to hurt your finite sample performance for the ATE. And this is something that I hadn't personally seen before and thought it was unintuitive. Of course, in practice, you're probably going to debias anyway because you need to get a confidence interval. So there's two competing concerns here, which are the finite sample performance and the uncertainty quantification. So this is not at all to say that debiasing is worthless. It's just that sometimes it helps your finite sample performance and sometimes it can hurt. So lasso looks a little different. For a lasso outcome model, you have some sparsity pattern where the sparsity pattern is based off of predicting your outcome y. In traditional undersmoothing, if you just chose a smaller lambda prime, two things would happen. One, you would shift all the coefficients towards OLS. And two, you would add non-zeros back in that are best at predicting y. So here you're undersmoothing in the L0 norm. You're making less sparse coefficients. Debiased ML, if we do double lasso, meaning that we have the lasso outcome model and we debias it with the lasso outcome model for the weights, that also shifts towards OLS. That's based off our result. But what we find is actually you add back in non-zeros that are best at balancing XQ. So you'll end up with a different sparsity pattern generally than if you just did the traditional undersmoothing of the lasso. And in fact, we recover the famous double selection result. So the sparsity pattern of the augmented model is the union of the sparsity pattern for the outcome model and the sparsity pattern for the weights. And that's how you get this difference. So this is kind of, we haven't done a lot of chasing down what are the implications of this result, but you can think of it as somehow for your target estimand, the traditional undersmoothing is not decreasing the bias in the right way. There's a more efficient way of decreasing the bias, which is much more targeted at the shape of 1 over E. So I think that this is an exciting direction to think about in the future. So let's do a quick summary. Machine learning is biased. There's two classical solutions. One is to do undersmoothing, where we just use less regularization. One is to do debiased machine learning. And our result is that you can think of these as both shrinking your original outcome model towards OLS, or unshrinking, I guess. And we showed in the special case of ridge plus ridge, these are actually numerically exactly equivalent. Our result applies pretty broadly. It can be linear in any types of features. So this includes the D bigger than N setting, or infinite dimensional settings like the RKHS case. Includes ridge, lasso, kernel ridge, principal component regression, but also honest random forests, or the last layer embedding from a pre-trained LLM. It doesn't include settings that are sort of fundamentally nonlinear. So if you were to do full pre-training, or sorry, like full fine-tuning of an LLM, then our numerical results wouldn't hold. When D is bigger than N, you have to be a little bit careful with the definition of beta OLS. It turns out that it corresponds to the minimum norm interpolant, and we talk about that in the appendix. Similarly, while in this talk I've focused on the mean, which is half of the ATE, identical results hold for other linear functionals. So you can choose any mean squared continuous linear functional. This result is still going to hold, but W hat is just going to estimate the Riesz representer of that particular functional instead. So there's lots of other stuff in the paper. We have illustrations on LaLonde and IHDP and a simulation study. And there's been many useful extensions to these basic results. So we considered what happens when you use sample splitting or cross-fitting. So this result, this shrinking towards OLS is all sort of in the same sample type phenomenon. So there's a question of what happens when you use cross-fitting. There's the question of what happens when you have a non-negativity constraint. So that's a minimal violation of linearity or general nonlinear weights. And we discussed that extensively in the appendix. I think our answer for non-negativity is very, very good. Our answer for the general nonlinear case is not as convincing, so there's more work to be done there. We provide an extension to the TMLE. So instead of doing AutoDML, you do AutoTMLE, and we sketch basically how you would get our same result in that setting. And then finally, we give an empirical Bayes interpretation of this unshrinking phenomenon in a variety of different Bayesian hierarchical models. So like I said before, this has been a generally fruitful setup. There are many downstream follow-ups, including multi-calibration to benign overfitting in the case where actually this debiased machine learning thing is going to be centered on the min norm interpolant. For synthetic controls is one example of a balancing weights problem, but it introduces the simplex constraints. And this result has allowed us to think of synthetic controls as doing sort of OLS, but with sample training. There are downstream applications of proximal causal inference, so extending our result to a full Fredholm integral equation instead of just a normal regression problem. And one that I've been thinking about a lot recently is comparing TMLE to debiased machine learning, where we can set up a finite sample comparison because you can always think of TMLE as solving a boosting problem. And so that directly allows us to think about how are we making the residual smaller in these two separate settings. So that's the main bulk of the talk. I can answer questions, and then I also have a numerical illustration, which I wasn't sure that I had time for. So I can take questions and then move to the numerical illustration.
Okay, perhaps we will take one question now,
Great.
as outstanding. So the question is, could you do the analysis also outside the L2 space?
Yeah, so we were, okay. Do you mean big L2 or little L2?
This looks like big L2. I'm not sure what exactly it
So
means.
for big L2, I don't think that we can. So we need everything to be in big L2 space so that we have overlap. So things need to be sort of like square integrable. We need the Reese representative to be square integrable, for example. And so that's a requirement that everything lives in big L2, but big L2 is a sort of insanely large non-parametric space. It's even bigger than an RKHS. For little L2, which is ridge, our paper is not limited to just discussing ridge. We also consider little L1. That's the double lasso result. And actually the main numerical result, you can do regularization in any norm. So you could do L infinity regression. I'm not sure exactly what that looks like. Usually people just consider L2 and L1, but yep, any norm is fine. Hopefully that answers the question.
Okay, we don't have any more questions now, so perhaps you can just spend a couple of minutes on the numerical result.
Yeah, so I'll just quickly, because I have a few minutes, we do a numerical illustration on the classic LaLonde dataset. So we consider both the short version of LaLonde with 11 features and the extended version of LaLonde with 171 features, and we do both double ridge and double lasso in the main paper. In the low dimensional setting, I mentioned the fact that as you move the regularization parameter for the weights to 0, you get exactly OLS, and sometimes that actually can happen for practical data sets. So for short LaLonde with the lasso, even with 11 covariates, you still regularize. That's the whole machine learning is biased issue. But we find when we do hyperparameter tuning for the weights, when you do cross-validation, you can sometimes get exactly 0. This is a little sensitive to the exact choice of folds that you use for cross-validation, which is a sort of a bad sign. There's some sense in which like this hyperparameter choice problem is still a little like numerically unstable or something like that. But one of the things that can happen is you can recover an exact 0. CVing prefers no Reese residuals. And so the final point estimate ends up just recovering exactly the OLS estimate. This isn't necessarily a bad thing. Like if you were actually converging to the weights very quickly with low variance, this would be great. This also guarantees that you're definitely unbiased, so your confidence interval is definitely going to be valid. But it's something that might happen when you weren't actually expecting it to happen. And so I think one of our things that we're trying to emphasize is you can think mechanically about what's happening when you do this debiasing procedure to make sure that you have clear eyes about what's going on. But I don't this is certainly not a negative result. It's equivalent to the OLS point estimate. In the high dimensional setting, it's basically never true, which makes perfect sense. So on the left-hand side, we have hyperparameter tuning for ridge and for lasso outcome models, and you choose a value of regularization that's greater than 0, of course. But for the weighting problem, which is this middle section, when you're doing the ridge and lasso Reese regression problem, you also choose delta bigger than 0. And that means that in general, the augmented point estimate is not the OLS point estimate. It's not the pure regularized one, but it's something that has less bias, but still less bias than the original sort of like lasso plugin, but less variance than if you went all the way to OLS, which is pretty important because you can kind of see that in high dimensions, anytime when your regularization gets really small, normally your variance starts to blow up. So that's why you don't want to choose delta equal to exactly 0. So yep, over here, choose delta not equal to 0, and then your point estimate is also somewhere in between. So yeah, that's it.
Thank you
Okay,
very
thank you.
much. Thank you very much for the great talk. Yeah, it's a good time to wrap up for both talks. We again thank both of our speakers for the very nice talks from 2 topics. So at the very end, let me introduce the talk for next week. So next week, we will have Vasilis Tsirkanis from Stanford University to talk about detecting clinical implicit biases in diagnosis using proximal causal inference. And we will have Ilya Spitzer from Johns Hopkins University as our discussant. And we look forward to seeing you again next week.